All right, this is the start of the next chapter, which is really part of the same unit on bonding. This is this part, the intermolecular forces part. So we're going to take a look at the notes here on liquids and intermolecular forces. All right, according to the kinetic molecular theory, or KMT, the attractive forces between gas particles for an ideal gas are negligible. We just assume that there aren't any. And of course, that's not the way real gases are, and we'll talk about that. But when we compare the properties of gases, liquids, and solids, we're going to fill in this table below about shapes and diffusion and densities and so on. Does it have definite volume? Well, gases, no. Liquids and solids, both yes. Does it have a definite shape? Gases, again, no. And now liquids don't, they can change their shape according to the container. Solids definitely have a definite shape. And does it expand to fill its container? Gases, of course, do. Liquids and solids do not. Is it compressible? Well, gases are, liquids somewhat, but not very much, and solids no. Do its particles flow readily? Of course, the answer to a gas is yes, and a solid yes. And gases and liquids, yes, but solids are no. Does it diffuse quickly? Gases, yes. Liquids, slowly. Solids can diffuse, but it is very, very slowly unless the temperature is exceedingly high. And what about its density? Gas has a low density. Liquids have a somewhat higher density, and solids typically a considerably higher density. All right, because the particles in a solid or a liquid are fairly close together compared with those of a gas, we often refer to these as condensed phases. All right, based on the information in Figure 11.2, describe how the intermolecular attractive forces appear to change as one moves from chlorine to bromine to iodine or iodine. And here's the Figure 11.2. So we're taking a look at the chlorine gas, bromine liquid, and iodine, which is a solid at normal temperatures and pressures that we would find. So we want to discuss how these attractive forces change. Well, obviously, the attractive forces increase as we go from chlorine to bromine to iodine because it takes a larger amount of energy in the form of heat to change the state from solid to liquid to gas. The kinetic energies of particles are usually controlled by changing the temperature of a substance. And we want to describe what happens to the attractive forces between water molecules as water vapor undergoes condensation, turning into drops of liquid water. Well, what happens is as the temperature of the water vapor decreases, the kinetic energy decreases. And this allows the molecules to get physically closer together. Once they get closer together, they experience these intermolecular attractive forces, which up till now have been negligible in the gas phase. And when that happens, the condensation occurs because the gas molecules are attracted enough to combine together to form a liquid. All right, in question G, we want to explain how increasing this pressure on a sample of gas can affect the attractive forces between particles. What happens is as we increase the pressure, this is an alternative way to bring gas molecules closer together. And because they're closer together, the attractive forces are no longer negligible, and so they become more effective, and the gas condenses. All right, now we're going to move to section 11.2, intermolecular forces. Question A says, how does the strength of these intermolecular forces in general compare with the strength of ionic, metallic, or covalent bonds? Intermolecular attractive forces are much weaker than intramolecular forces. And we're going to refer to the diagram at right. Okay, we have a little diagram here of a collection of hydrogen chloride molecules, and we want to discuss the differences in strength between these attractive forces, which we've labeled as A and B. All right, A, these bonds here, these are the bonds between the hydrogen and the chlorine in a molecule. These are covalent bonds. These are intramolecular forces. They are forces inside the molecule or between atoms that are bonded together. The attractive force labeled as B is intermolecular force. These are forces that exist in between different molecules. And we can know that force A is considerably stronger than force B. It takes quite a bit more energy to break these intramolecular forces than it does to break intermolecular forces. So in fact, the next question asks us to explain how the data in the table supports my answer to part B. And here we actually have quantitative results. We have numbers we can look at to determine the answer to this question. So we need the enthalpy of vaporization, and that's only 16 kilojoules per mole. It doesn't take that much energy to turn liquid HCl into gaseous HCl. We haven't broken the bonds between the hydrogen and the chlorine. We've just turned it from a liquid into a vapor. However, if we want to break the bond itself and break it into hydrogen and chlorine gas, that's altogether a different story. And that requires a considerably larger amount of energy. And if I divide 431 by 16, I get a number that's roughly 25 times as much energy. And the reason for that is because these bonds between covalently bonded molecules, they're just pretty strong, and it takes a lot of energy to break these apart. All right, now the next question asks us what conclusions can be made about the relative strengths of attractive forces from the information in this table. And this table is a little list of melting and boiling points for different kinds of compounds. Okay, so what we can see when we look at this is that the melting and boiling points for the first three compounds are significantly higher. And so there's considerably more energy has to be added to break these bonds than to break the intermolecular attractive forces holding together the bottom three molecules. It doesn't take much energy at all to turn solid nitrogen into liquid nitrogen and then to boil that into vaporous hydrogen and so on for these other gases. But it does take considerably greater energy to melt ionic and metallic bonds. And therefore, we can conclude that the intermolecular forces are much weaker than the intramolecular forces. Question E says to name 3 types of intermolecular attractive forces. Okay? And so these we're going to get very familiar with. These are London dispersion forces, the dipole-dipole forces, and the hydrogen bonding forces. Okay? Now, question F asks us to give a brief summary of how these electrostatic attractions are affected by the magnitude of the charges and the interparticle distance as it relates to Coulomb's law. So here is what Coulomb's law says, and I think you all of you know this, that the force is equal to some constant K times charge 1 times charge 2 divided by the distance between them squared. So what we can say that the attractive forces increase as the charges increase, and the attractive forces decrease to the second power as the distance increases to the first power. So question G says, based on your answer to part F, give 2 specific reasons why intermolecular forces are weaker than ionic bonds. Okay, well, that's because the charges are smaller in magnitude and the distances are greater. And that makes the numerator smaller, the denominator larger, and that just makes the force considerably smaller. Here's a little summary. This diagram is not in your notes, I don't think. So if you want to take a look at this, you can. This is just telling us, when we talk about ions versus polar molecules, what types of these van der Waals forces are in play, which ones are the weakest, which ones are the strongest. So you can see on the left, these LDF, these dispersion forces, are the weakest intermolecular force, going up through dipole, hydrogen bonding, ion dipole, which is sort of a subcategory of dipole, and then the strongest force would be the ionic bonding. And we know that's true because the temperatures for melting and boiling are the highest for these compounds. All right, in 1930, Fritz London proposed that the motion of electrons in an atom or in a molecule can create an instantaneous or a momentary dipole. So London dispersion forces are not named after the city of London. They're named after the man named Fritz London, who came up with this effect. He was a physicist. All right. We want to describe what can happen in an atom or a molecule when the distribution of these electrons can be arranged asymmetrically, even for just an instant. Well, what happens is the motion of these electrons in one atom or molecule can affect the motion of electrons in a neighboring atom or molecule, and the instantaneous dipole, which is a result of this motion, can induce an instantaneous dipole on another molecule. Now, we want to define the word polarizability, and we want to explain how this property is related to the relative strength of dispersion forces. All right? The polarizability is the ease with which the charge distribution is distorted, and it's related to the size of the electron cloud on the atom. All right? And really, we want to go back to the word polarizability. And of course, the root of this word is polarity. And polarity, from a physics perspective, means the property or characteristic that produces unequal physical effects at different points in a body or a system. Okay? So that's what's happening inside the molecule. Now we're going to use our answer to part J in the previous question to explain the boiling point data that we see in this figure. We're comparing neon, argon, krypton, and xenon, and then again to the halogen gases in blue. So as you move down a group, 17 and 18 in this example, the electron clouds are larger, they're further away from the nucleus, so they are more easily polarizable. This allows a greater dispersion force. A larger amount of energy has to be added to overcome this polarizability and therefore to cause melting and boiling. Now I've got a note in your notes. This is important. I'm just going to read this verbatim. The polarizability of a molecule and the dispersion forces generally increase with the size of the atom or molecule. So when you compare two substances on the basis of their LDFs, you should always talk about the size of the electron cloud and the polarizability. Do not explain a boiling point trend by saying that X has a higher boiling point than Y because it has a greater mass. That explanation would be incorrect. It's not about the mass, it's about the polarizability of the electron cloud. Mass does follow polarizability, but this is not a gravimetric issue. It's a polarizability issue. With that, we're going to stop this section and go pick up in another video.